All right, well, as people are filtering in, we are getting started and ready for our very last round of talks in this workshop. Round number 4 is going to be 2 different speakers, and we're going to be talking about methods of looking at the deep ocean. So our first speaker is going to be thinking about observations, and our second one is going to be thinking about models. And as before, we'll have 2 20-minute talks and then some time for discussion. And then after a bit of a rest, we'll have a breakout where we can all talk about this together. So our first speaker is going to be Nathalie Zilberman, who's a researcher at UCSD and Scripps. So take it away.
Thank you. I'm just going to share my screen. Could you confirm that you can see it okay?
Not yet.
Oh, wait, hold on. Can you or not?
We can hear you. We cannot yet see your screen.
Okay. Should be better.
There we go. Okay.
Better. Okay.
You are in, yeah, there we go.
There you go. Okay. Okay, good. All right. So I'm going to talk about some steps towards a global and interdisciplinary deep ocean observing system. So first off, I thought we could take some lessons from what has been shown to work pretty well. Those are keys to success from the Argo program, and I think those can be easily applicable to what we're trying to achieve here. First off, whether you're a biological oceanographer or physical oceanographer, it's safe to say that what we're looking for is a global full depth coverage. It's important that we reach a consensus among the scientific community of the objectives that we're trying to achieve, and that we have the support from the agencies. This ocean observing system should be synergistic, well integrated, and multidisciplinary. And then the resources need to be available for this system to be sustainable. Needs to be well documented. The data needs to be freely available. And the technology needs to be fit for purpose with a diversity of commercial providers in order to not running out of platforms and sensors. And finally, products should be made available for the data to be easy to access and use for people who are not familiar with it. So looking at the state of the deep ocean observing system below 2,000 meters, I'm looking at what physical oceanographers refer to the deep ocean. In terms of observing systems in place below 2,000 meters, we really are just looking at GO-shaped ocean sites. And Deep Argo, there's only 10% of historical data set that extends below 2,000 meters depth. And Deep Argo, in less than 7 years, have managed to collect about as many profiles as from historical data in over the past 70 years. So quite a big achievement. You can see in the top figure here, those regions where Deep Argo floats have been deployed, and then the color in the historical data in the bottom panel and on the top are the same. So Deep Argo is well integrated within other deep ocean observing systems, including GO-ship and ocean sites. And in addition, Deep Argo floats can provide data during the winter time, which provides seasonally unbiased data, which is very important. So the straw plan for the Deep Argo array, the objective is to reach that 1,250 Deep Argo floats. We are quite far from it yet, but a lot of progress has been done that we'll talk about. The size of the array was defined to reduce the uncertainties in trends of ocean heat content and deep steric sea level by about a factor of 10. Right now, the uncertainties are about the same size of the signal, and the goal was to reduce these uncertainties so that they are about 10% of the signal. And in order to reach that global Deep Argo array, 300 floats have to be deployed every year. And I refer to that implementation paper that has been published last year that has a lot of details. So the objectives of DPAGO, as I said earlier, were very clear. The first one was to reduce the uncertainties in ocean heat content. And you can see here in this figure that the amount of heat accumulated from the atmosphere into the ocean has been accelerating over the past few years. And it's very important for accurate projections that we reduce those uncertainties. This is a proof that DPAGO can indeed reduce those uncertainties. If you look at the top two panels, in the red are the uncertainties in trends of ocean heat content in the Argentine and Brazil basin, in red from historical data, and in blue from DPAGO. And you can see indeed that the spread, especially seen here in the Argentine basin from historical data in red, has been greatly reduced using DPAGO in blue. Other interesting factors are this acceleration in ocean heat content in the Southwest Pacific basin that has been observed, and that reversal from warming to cooling in the Armenian Sea. So the other objective was to reduce uncertainties in deep steric sea level. We all heard about this non-closure of the sea level budget since 2016. The question is to whether this non-closure is due to drift in sensors from satellites or from in situ data. But another important candidate, is the fact that we are not monitoring the deep ocean steric sea level. So this is a paper in PrEP that is showing the difference between upper steric sea level in green and in blue deep steric sea level. And you can see that fluctuations are, there's a factor of 2.5 in front, but regardless, you can see that those fluctuations are different. So you can see that the forcing driving the low, upper, and deep oceans are different. So having the upper steric doesn't tell you about necessarily how the lower steric is changing. So it's important that you measure both. And another objective from DPAGO is to reduce uncertainties in numerical model prediction. This is showing that when using only core and deep, you have significant differences in errors. So a great reduction in errors in temperature and salinity below 2,000 meters when you simulate DPAGO flows. And so this is another proof that DPAGO can be very useful for numerical models. Here we're looking results from Mitchell-Chandler showing the seasonal variation below 2,000 meters of dynamic height in the Southwest Pacific Basin and comparisons with Loris. And you can see this ocean reanalysis shows the colors. The color bar have a factor of about 3 difference. And you can see that the signal has been greatly reduced in the ocean reanalysis, and there's a 2-month lag. So DPAGO can provide really great information for validating ocean models. And there's a new objective that has been added to DPAGO, is to measure ocean bathymetry. All floats are measuring to the ocean bottom, so they can feel the bottom, and from that you can make great measurements of bathymetry that have been validated against multi-beam, which is the best estimate that you can have of bathymetry at the moment. So this is using all of the global Argo data that has been collected, over 10,000 measurements of bathymetry. You can see this great correlation between multi-beam and DPAGO, which proves that DPAGO is a great way to measure ocean bathymetry. And here you can see the differences from the Smith and Sandwell bathymetry between using and not using DPAGO. And DPAGO has now been added to the JEPCO grids as a new source of bathymetry. So I think it's important that we're looking back into the different stages that Argo is following when adding new sensors. And so what is referred to stage 1 is when there's a deployment of less than 10 floats. Stage 3 is when methods for doing quality control of the data set are starting to be implemented. The sensor has been approved by the Argo steering team, and there's about 100 floats or so that have that new sensor. And stage 3 is more like the global implementation, where the quality control method have been fully implemented, and when there is a new parameter, it has been approved both by the Argo steering team and the IOC. So there are new applications for Deep Argo that are under testing. Oxygen sensors have been implemented of about 30% of Deep Argo floats. It's currently in stage 2. Ocean mixing and ocean scattering are still in the prototype level. So the status of the Deep Argo float array is shown here. Now we have about, I think we have 11 countries contributing to it, which is great. About 200 floats are active. There's a plan for deploying about 100 each year, which is fantastic. And the goal is to maintain those arrays in those deep regions that are mostly deeper than 4,000 meters or even deeper than 5,000 meters. They are shown in the gray colors, but also to start extending those regional arrays, and especially in the North Atlantic and in the Pacific Ocean. And then the next step will be to deploy on a global scale. So just a little schematic showing, the cycle of a Deep Argo float. It's very similar to core Argo. The only difference is that the measurements are from the seafloor all the way to the surface. So there are, as I talked about earlier, it's very important to have different providers building different platforms and different sensors, and that's to avoid any interruptions in float or sensor production. So right now there are the different models that are active at 4,000 meters that can go to 4,000 meters or 6,000 meters. Most of them, 70%, can measure to 6,000 meters depth. There's additional float models under development. And the average Deep Argo float lifetime among all float models is 4.7 years, which is a little less than the 5.5 years for core Argo, the upper 2,000 meters Argo, but great technology development is ongoing, and the goal is to increase further the longevity of the Deep Argo floats. So I talked about float models in terms of CTDs. Argo is limited by CTD providers. That's not only for Deep Argo, but for core Argo as well in terms of temperature and salinity measurements. There are 3 CTDs currently active, 2 from Seabird and 1 that is under testing from RBR. One of them, the SB61, has reached the target temperature and salinity accuracy. 2 have reached actually the salinity accuracy level of 2 × 10⁻³ and pressure sensors are under development for increasing the accuracy of pressure from 4.5 to 3 decibar. So I thought it would be useful just to add some recommendations for Argo data use for people from the audience that are not too familiar with Argo. The recommendation is to please refresh your Argo data set frequently because an Argo profiles has been quality controlled. Doesn't mean that it will not be quality controlled again. Argo is a living data set, so please make sure that you have the most recent data set in your analysis. There's different ways to download the data. You can just download it using the DOI. You can rsync it. You can RDAP it, and there's also there's a great selection tool from your Argo that is shown here that is very simple to use when you can just grab the data based on the platform that you want and the time period that you're interested in. I talked about Argo product. It makes it very easy to use the Argo data, but please make sure that you understand the data that has been used in the product. And if you're not too sure, make sure to contact an Argo person who will tell you. So there has been great progress in Deep Argo in terms of quality control. There's now about 81% of the salinity profiles that have been corrected that have an accuracy of ±2 × 10⁻³, which is fantastic. 69% of the real-time data set is now adjusted, and ongoing work is focused on bringing the quality control of the data set even further. So this screenshot is showing the argo.ucsd.edu website. This is the official Argo website, which has a great amount of resources in terms of whether you're trying to learn about the way Argo is organized, the data set that is available, technology or outreach material. So for instance, here, if you click on data and data product, you will have a whole list of the products for temperature and salinity and velocity. So it's a great resource because those are products or knowledge that are agreed with the Argo community. So something interesting from Deep Argo is that there has been a switch from publications that focused on technology to science, as you can see here to the right. So the technology has been demonstrated, and now the science has shown that Deep Argo is able to reduce the deep ocean signal, which is a great achievement. Just please make sure that you refer to the citations of Deep Argo or One Argo or Argo data. Those are shown here, because it helps the Argo community keeping track of how the data is used and who uses it. So it's very valuable to the Argo community. So please make sure to do it in your publications of products. So the current challenge, people have talked about this for the past couple of days, is that One Argo is not funded. Argo groups have use a lot of resources for the Deep Argo and the biogeochemical Argo extensions, and as a consequence, the core Argo, the upper 2,000 meters, have suffered with the net decline. So we're hoping that with the support of the scientific community, funding agencies will provide additional support. So to conclude, in terms of data use and access, Argo is a living data set. Just make sure that you use the most up-to-date version of the data set. There are products that have been developed to facilitate the use of Argo. I showed them on the Argo website, and new Argo are under development. And please make sure that you cite the publications so that the Argo community can keep track of the data use. In terms of objectives and status, Deep Argo has shown that it has the ability to very rapidly identify deep ocean observation, that the technology is fit for purpose, the deep ocean signal and temperature salinity can be resolved, and also for steric sea level. But the resources are limited. Only 15% of the funding for the global implementation of Deep Argo is available. And to finish, there are 4 Deep Argo float models that are currently available, 2 additional under development. The CTDs are performance are now edging the target of accuracies and stability, which is wonderful. And additional objective of measuring bathymetry have been implemented, and there's new applications that are under testing, which includes oxygen measurement, ocean mixing, and scattering. And that's it.
All right, thank you very much. Our next speaker and last speaker is going to be Henri Drake, who is a professor at University of California, Irvine, and will be talking to us about modeling.
Great, thanks for the introduction, Zach, and thanks for setting up my talk, Nathalie. Can I advance these? Yeah, okay, great. So I came up with my own little schematic for the different types of pathways, or at least how I think about them. So I think about oceans that look like this, that are somewhat simplified. And the black lines here are density surfaces. And so I really think about kind of 3 qualitatively different physical pathways to the deep ocean. So one is the mean overturning circulation, which I've shown here in green. Think about this as Antarctic bottom water entering the abyss. In purple is isopycnal transport, which actually goes along density surfaces, but can be opposite the direction of the mean circulation. So tracers can still get into the deep ocean even if they're opposing the mean circulation. And then finally, there's the dipycnal transport, which is crossing density surfaces, and there needs to be some material process that changes a water parcel's density for that to happen. So, right, those are just the names of those. And if we want to actually model this circulation, we have to make sure that we're modeling the processes that contribute to each of these 3 different pathways. You also can think about the inverse problem, as people have already mentioned, which is how things at the bottom of the ocean get into the deep ocean and then back up to the surface. And the methods that you use to diagnose these two different pathways are not necessarily the same. So the methods that we use to analyze models need to really be tailored to the question at hand. So the other thing I want to mention about this is that this is not necessarily a symmetric process, in the sense that if we are thinking about the pathways that connect this blue star at the surface, say in the Southern Ocean, to this star at the bottom of the ocean, the abyss in red, the pathway to get from blue to red might be a quick deep convection and transport pathway that takes on the order of 10 years. But then for that signal at the red star to get back to the surface could take thousands of years on a very slow diffusive pathway. So if we're trying to track things doing these kinds of circuits, we have to take that asymmetry into account. So I want to mention 3 different methods that we use in models to understand these pathways. And because Gökhan gave such a nice overview of modeling in general, I'm focusing on really diagnostic methods, meaning once you've run a model or when you're running a model, what other tools can you use to understand the pathways in those models besides just kind of running it? So the first of these methods is just kind of any type of Eulerian tracer method. By this, I mean that we have some tracer of interest. Think about this as your favorite biogeochemical tracer, for example. I'm calling this lambda for generality. So we're interested in how the concentration of this property in a water parcel is changing over time, which is the material derivative. And that includes both local time tendencies, so how does the concentration change in one grid cell, as well as advection, so how that's getting moved around in the ocean. And then in addition to that, there's also the fact that as it's traveling around in the ocean, there can be transformation processes that change its concentration. Those could be physical, such as mixing, or fluxes from the boundaries of the ocean, as well as biogeochemical processes. So there's 2 different types of tracers which act quite differently. First, we have active tracers, such as temperature and salinity, which contribute to density, and density is felt on by gravity, and so affects momentum of the water and feeds back on the velocity. That is very different from all these other tracers we've heard about, which do not affect the circulation. So anything from chemically inert transient tracers to idealized tracers like ideal age. These things, very interesting, very useful to trace pathways. They don't actually affect the physical pathways themselves. I'll just give examples of 2 of these. So the first is these chemically inert transient tracers, which we already saw in both Gökhan and Jake's talks, and Sarah Perky's. Yeah, so we have CFCs, for example, which are this, they peaked in like the 1980s and have gone back down. So there's this interesting pulse as a boundary condition in the atmosphere that we can trace into the interior. And so this is kind of what those time series might look like. And so in a climate model, we can impose these as boundary conditions at the top of the ocean and then simulate how these get advected and mixed down into the ocean. So in this case, I've run the GFDL model at a very high resolution, 1/8 of a degree, with a projection for what the CFCs might do over the next few decades. And so this is, I think, just a time slot in the 1990s around when the GLODAP survey was taken, comparing on the top panel the zonally integrated inventory from the observations. So you're seeing these big plumes of CFCs coming in at high latitudes where the deep waters are formed. And you can see, as was already mentioned in Gökhan's talk, that the model, in this case the GFDL model, is not penetrating deep enough in the North Atlantic. So our AMOC is not getting to that 4,000 meter depth that shows up as this plume in the observations. So this can be a very useful type of diagnostic for evaluating ventilation in the models. So in model land, we're not restricted to tracers that are observable. We can also just make up our own tracers, and this can be very useful. So one of them that's been used a lot is called ideal age. Ideal because this doesn't actually exist in the ocean as a thing you can measure, although radiocarbon maybe tells you about this. So it's very simple. Its initial condition is that the water at the beginning of the model has an age of 0, and then it gets older by 1 second per 1 second of simulation time. And then, so that it's not just uniformly aging, we set the boundary condition at the top of the model where it touches the atmosphere to a constant age of 0. And so essentially, it's constantly being reventilated or being reborn at the surface, and this age deficiency is propagating down into the ocean. What's nice about this is that at equilibrium, you can interpret the equilibrium ideal age as like a time since ventilation. And so I think Jake Gebbe already showed some maps of this from his model, but in a climate model, you can do the same thing. So this is an old paper by Matthew England, where he shows that the North Pacific has these 1,000-year-old waters. Yeah, so the problem, as Gökhan already alluded to, is that we actually typically don't run these models to equilibrium, so we cannot interpret it as this time since ventilation usually. Instead, you can still look at how the age tracer evolves once you initialize the model. And so here I've come up with this transient age deficit parameter, which is basically the time of the model since initialization minus the ideal age divided by the time. And the way to interpret this is quite simple. If it has a value of, one of those should be 0, but if it has a value of 1 or 100%, that means that it's very recently been ventilated. 0 means it hasn't been ventilated at all. And so if I play this movie, you can see these large, high values of freshly ventilated water propagating through the ocean. And I'm showing the colors here for the bottom grid cell of the model. And so you can really see, let me play it again. You can see these bottom waters propagating mostly from Antarctica, but also a little bit in the North Atlantic. And so this is useful not to validate the model quantitatively because we can't actually observe these, this tracer, but by comparing two different versions of the model, you can get a good sense of whether you've improved or made ventilation worse. So the second type of method is Lagrangian particle methods. Can you turn the clock towards me so I can see? Sorry. Thanks. Okay, so Lagrangian particle methods, instead of the Eulerian tracer approach where you're fixing a box measuring the concentration of something, instead you follow water parcels around in a model. So this is a movie I made in the Antarctic circumpolar current with 5 particles. You can see this one got trapped in an eddy, which is pretty cool. And yeah, so there's this review paper that's really useful for the details of like how you actually implement this. But I'll just show kind of 2 different applications. So the first is what I'm calling the mass volume transport stream tube approach, which is the idea that mass or volume is conserved along a parcel. And what's nice about this is that we already have velocities from an ocean model. We can just integrate that over time to get the evolution of this parcel's trajectory and know that it carries its mass along with it. And from that, you can actually do some pretty cool things. So this is a really nice paper by Matthew Thomas where he first calculates the overturning stream function in the North Atlantic using the standard Eulerian method. But then he does the same thing using just Lagrangian particle trajectories. So here, this is a purely Lagrangian calculation where he is tracking millions of particles that are tracing out the trajectories of the overturning to, in an integral sense, when you add up all of those particles, they give you the same overturning stream function. What's really cool about the Lagrangian framework is that each of these particles follows a different trajectory, which means now you can do conditional averaging or conditional summing. And so in this case, you can decompose the overturning based on where the source waters are. So here he's cut up the North Atlantic into the different source regions and shown the overturning stream function that for the waters that are ventilated in each of those regions. You can never do this with like a normal Eulerian calculation, but you can do it with this Lagrangian one. Super cool. Another thing you can do is make really nice visualizations. So this is a movie I did when I was working with Veronica Tamzit and Nathalie on upwelling in the Southern Ocean. And here I've released a bunch of particles at 30 degrees south in the Southern Ocean, and you're seeing them upwelling, changing their colors as they come to shallower depths around Antarctica. And so, yeah, it's just really nice for tracking and kind of tracing out these different pathways. In this case, one of the things we found was that the pathways are actually very sensitive to model resolution. So I did the exact same particle tracking in 2 versions of the model, one at 1 degree with no eddies, so just parameterized eddies, and then one with an eddy resolving model. And what you can see is not only are the pathways kind of quantitatively different in that there's some different shading here, but actually some pathways are just straight up not in the low resolution model. So all these ones along the eastern boundaries are not showing up in the 1 degree model. That includes a pathway that's off the eastern or western coast of Australia that Sophie's poster was showing some observations of. So this, is like qualitatively different at different resolutions. Another thing you can do with this Lagrangian analysis is also look at the timescales of these pathways. So this is a paper by Rousselet et al., where they traced out the timescales of different pathways of the overturning circulation. And so you can see here at the bottom that the abyssal cell is really, these particles are taking thousands of years to make the whole global overturning transit. Okay, so that was this mass stream tube approach. When you want to compare, or when you want to think about tracers and the pathways tracers are taking, those are actually not materially conserved because mixing is acting, or molecular diffusion and turbulent diffusion are acting to diffuse those particles. So it's more of a Brownian motion thing. And so if you want to use Lagrangian methods to understand a tracer, you have to really account for that diffusion. And so you can do this using either Ito or Stratanovich calculus. And now you have to basically solve for the stochastic trajectories of every single particle. And only when you have enough particles and you add them up, can you reconstruct the tracer. So here with just 1,000 particles, you get a kind of noisy version of the Eulerian tracer distribution. But once you go to 1 million particles, you get basically the same answer as the Eulerian calculation. This is really cool, but it's kind of technically really challenging to actually implement this Brownian motion in a way that you get exactly the same solution. And as far as I know, it's never been done in a climate or ocean model to reconstruct a tracer distribution using only Lagrangian information. But this is something that we should do. Okay, and finally, the last method is what I'm calling semi-Lagrangian water mass analysis. It's semi-Lagrangian in that you can be Lagrangian in one dimension, like the vertical, but Eulerian in the horizontal in some sense. And so the way this works is that we can consider a water mass, which in this case is defined by bounds of a tracer within a region. So think about this as like the water that is colder than 1 degree Celsius. So that's like a definition people have used for Antarctic bottom water. And so the question is, if you calculate that water mass, so just figure out all of the water on Earth that is colder than 1 degree Celsius in the deep ocean, define that as Antarctic bottom water. The question is, how will that mass of water change over time? And so what we can do is just a mass budget for that layer of water. And to close the mass budget, we need to essentially calculate the fluxes across each of the boundaries of our water mass. So that includes in blue the surface. So if Antarctic bottom water comes up to the surface in Antarctica, we have to account for fluxes of water directly into the water mass there. If it gets exported from, say, the Southern Ocean, we have to take into account the horizontal transport as it's exported. And then finally, if there's some interface within the ocean, say between Antarctic bottom water and deep waters above, we have to take into account how that interface, that density surface, moves. What's nice about the water mass transformation analysis approach is that the movement of that interface, you can actually also think about not in terms of just the movement of the interface, but the density changes or the temperature and salinity changes that change material density and cause the surface to move. And so you can look at the math in my paper. I don't have time to do it now, but you can write these really nice budgets that relate the mass budget to the transformation processes that change water mass density. And so that includes things like mixing, surface fluxes, and ice-ocean interactions. So it's pretty hard to interpret this. Let me go through an example. So one of the terms in the budget is the overturning. And if you define your water masses correctly, so using density as kind of the tracer that delineates the water masses and latitudes as your regions, one of the terms in the budget is just the overturning circulation in density coordinates. But then, so the way the budget works is we're doing a mass budget for all the water that is denser than some isopycnal and that is southward of some latitude line. And then the overturning is just the transport laterally across that latitude line. But the nice thing about this approach is that if we do it for a whole bunch of different latitudes and densities, we can actually decompose the overturning circulation into all these other processes that contribute to it. So for example, the surface flux is creating dense waters in both the North Atlantic and the Southern Ocean. And then the mixing term is acting to transform those waters back into lighter waters, for example. And I don't have time to go through this whole example, but I'm happy to talk about it. Okay, and this kind of confirms things we already know, but does it in a more quantitative way. So to summarize these three different approaches, we have Eulerian tracer methods, which are really nice. One, because we can directly compare them to observed tracers, but also we can be creative and make these custom tracers that tell us information that we can't get from tracers in the real world. They're also nice because they're just a really direct method. You just have to add a tracer to your numerical model. The problem is that numerical model computational complexity basically scales with the number of tracers. So if we wanted to satisfy everyone's desires and add a whole bunch of tracers, the models would get really expensive. Yeah. So for Lagrangian methods, they're really nice because you can conditionally average these pathways kind of based on where they go and what their characteristics are. And that can be really useful to separate out distinct pathways that from a tracer would just look like they're kind of all mixing together and really diffuse. Another benefit of Lagrangian methods is that you can just use existing data output, so the velocity fields of a model, and do calculations offline without having to rerun the model in the first place. And the downside of this, or the gap, is that these methods are often used in a really qualitative way, which is difficult to quantitatively connect to observations. Okay, and then finally, there's this water mass approach, which is really useful because you can do these process-based analyses of water mass changes and circulation. And a difficulty is that they require these dedicated diagnostics that are not really available on things like the CMIP archive. So just to summarize, the challenges are that interpreting the results from each of these methods is really challenging when both the circulation and the tracers are rapidly changing. And so you have two trends that can be hard to pull apart. And most of these advanced diagnostic methods have really mostly been used on like pre-industrial circulations or historical circulations with the kind of implicit assumption that the circulation is steady and that the tracer boundary conditions are pretty straightforward. Another challenge is that some of these methods don't necessarily correct for model drift, or if the model has sufficiently large biases, they give you kind of meaningless results. And so maybe we have to somehow correct our models for those biases before running them through these kinds of calculations. In terms of opportunities, a lot of these methods now have like codes that can be used by the community to generate new analyses, and there are best practices that have been developed for how to do this. Another thing in terms of opportunities, almost done, is that CMIP7 efforts are now underway. People are starting to plan the next generation of models. So if there's a diagnostic that we really want to have in terms of the deep ocean, I think now is the time to advocate for that. And that goes kind of the same way with observations, that we want to be using observations to evaluate these models and inform their development, which is also underway. And then finally, what I really like about these three methods is that there are observational counterparts for each of these types of calculations. So for Eulerian tracers, that's pretty obvious. If you measure a tracer concentration in the ocean and that tracer is simulated by your model, you can directly compare those values. For Lagrangian trajectories, there are Lagrangian observation platforms, which can be used to directly compare trajectories in the model with some caveats. And then finally, water mass budgets. Those are a bit more complicated because there's many terms in the budget, but actually we have ways of observing pretty much all of them except the mixing term. So if we assume that the budget's closed, then we can infer the mixing transformations as a residual. And finally, I'll just finish by saying that DeepArgo is the only observing platform that can be used to validate all three of these methods. So I think it's kind of a uniquely useful observation platform, and it should definitely be funded going forward.
All right, we have time for some questions. If we can put Nathalie back up on it. Thank you. Yeah.
This is related to funding and the costs with DeepArgo. I knew the numbers before the pandemic with biogeochemical Argo cost and DeepArgo cost. And I mean, we talk about the funding challenges, but could you give us an estimate of what one Argo float cost is?
It's about 80 to 90 million for the international one Argo program per year.
Per year, so 80 to 90 million per year for
yeah. Whether it depends whether you include in it the resources for quality control or if you just consider a hardware, meaning float production. But roughly 90 million is a good rough back of the envelope estimate.
Okay, and then just if I compare it to the Cheyenne or retro computer that we have right at NCAR, that is about, I think, $40 million range for about 4.5 to 5 year lifetime. So it is, I guess, I don't know, just a comparison.
It is very cheap. Argo is extremely cheap for providing top to bottom interdisciplinary with BGC and top to bottom temperature and salinity with core and deep. It's not even the cost of the sensor on a satellite per year.
Compared to satellite, thing is,
yeah.
Yes.
So it's very cheap for what it can do.
You should provide the cost per cubic meter in the ocean.
That's it. Actually, you know what? That's a good one. I make a note of that.
Online question.
Yes, from Maria. Maria, you can go ahead and unmute.
Hi. Yes. Hi, I have a question for Nathalie. Maybe you have mentioned, but do you know if there are deep Argo float with the chemical sensor? If so, from when?
So there are, thank you, Maria, for the question. So there are deep Argo float with oxygen sensors. About 30% of them are equipped with oxygen sensor. This is an effort that has been initially led by the French groups. And so that's why most of their floats are equipped with oxygen. There's a lot of work right now in terms of the performance of the oxygen sensors. And the path that I shown you, those stage 1, 2, and 3, right now oxygen is in stage 2, meaning that there's still work to be done in terms of developing a quality control method, but also with the sensors themselves. So right now the sensors have the ability to resolve the spatial variability of the deep ocean signal, but they don't quite have the ability to resolve the trends in oxygen. And that's because the accuracy is not high enough yet, or they're not quite as stable as they should be. But there's ongoing work from all the oxygen sensors manufacturers, I think about 4 of them. And so it is the hope that soon more floats will be equipped with oxygen when the technology will be ready. And there's development work right now to to test, I should say, scattering sensors onto deep Argo floats, but those sensors have only been tested on CTD-CAS. They haven't been implemented yet, and that's something that the Italian group is working on.
Okay, thank you.
Yeah.
Question for Henri. 2 questions. In CMIP 6, what diagnostics you would like to see the most model to include in terms of water mass transformation, for example? And what tracers, additional tracers, you think would be the most useful to carry in as many models as possible?
You mean in CMIP 7?
CMIP 7, sorry.
Yeah, thanks. So in terms of the water mass transformation analysis, you need full closed mass and tracer budgets. So for whatever tracer you want to do the water mass transformations in, you need a full budget for that. So the difficulty with this is that they're latitude, longitude, depth, and time resolution. So they're big data. So they're not output by default. So temperature and salinity, for example, I think the vertical integrals are always output for every model in CMIP 6. And then the full 3D budgets are only output as part of FAFMIP at like a low priority, or I think they're output at annual mean resolution, which is not good enough for doing these kinds of calculations. So my recommendation would be to either have like a dedicated MIP that would output these kinds of diagnostics just for maybe like a short term or averaged in some way, or to output them at, so we've done some experiments in the high resolution model at GFDL where it was output at coarser resolution, but in a conservative way. So you're still closing all of your budgets, but you're reducing the size of the data substantially. So that could be an approach going forward to still have basically the same information, just at less diagnostic resolution, but that doesn't actually affect the quality of your analysis. So models should be closing their tracer budgets anyways. So if you're not, then that's a problem. And if you are closing your tracer budgets, then it should probably be pretty easy to implement these kinds of diagnostics and output them. Certainly everyone already does it for temperature and salinity, and then they should be doing it for biogeochemical tracers, I think, as well.
And then you can remap that on density and do.
Yeah, it's all, everything else after that is, we have tools for doing that kind of automatically now. We just need the data available. And then your second question was about
tracers
Yeah.
of ventilations. Would you like to see CFCs
Yes,
or
the
ideal
CFCs,
age or
I think-
radiocarbon? What is something that would be very useful in your mind?
I think ideal age is already pretty standard, but CFCs are not being run by most models. And so
They should be standard. I mean, in OMIP, I think we asked for ideal age, CFC 11, CFC 12, and SF6.
yeah, but that's
But asking for them is one thing, and whether the modeling groups are doing it, another thing. So
yeah. Also, having it in OMIP is one thing, but having it in a couple of models is another thing. And I think
yeah, but they should have followed the same sort of list. Well, ideally.
yeah.
And I actually have a question. All right, here's the challenge for you, Henri and Nathalie. Okay, so Henri, you obviously really want some deep Argo data, right? And Nathalie, you obviously really want to put deep Argo in the water. So what type of funding mechanisms, this is for the whole group actually, how do we do this where we have explicit source of relevance and need? Like, is there a way that the modeling community and the observing community can go in on a proposal together to make sure to get deep Argo funded?
Yeah, I can go quickly. So I was actually, when Nathalie was talking, I was looking at the map of where deep Argo is deployed, and I was projecting on that our map of biases in the GFDL models. And there are places where we have big biases, but there's no deep Argo floats. So maybe, that's a way that we can write collaborative proposals and try and target specific regions where we need that data to constrain the models better.
Yeah. So many would go to the modeling efforts, but you can't do the modeling efforts until we better constrain it.
Yeah, no, there's and actually in Henri, there's a lot of discussions that have been done during the Argo Steering Team meeting about a month ago, and actually the plan for Deep Argo is to organize meetings with modelers for having a best strategy for transitioning from regional pilot arrays to global implementation. So I might take you up on the offer and invite you to one of those meetings. We would love to have the feedback from different modeling groups into where would be the regions where you would have most interest, where would our modelers more interested in a global distribution of a sparser? Would you be more interested in having maybe 200 and 400 floats more sparsely distributed over the global ocean, or is there some key regions where you think that before transitioning to a fully, implemented 1200 float array that you would like to have data first? So, I think we should talk after the meeting and discuss this, because it's quite a priority for DeepArgo right now. In terms of funding, I think those type of proposals could be great because they can boost up a global implementation. It's important for DeepArgo to be sustainable, meaning, it's not the best to have full deployments for only 4 or 5 or 10 years. I mean, 10 years would be fantastic, but even 5 years, it's not great, because then you have great deployments and then so what happens? But sometimes it can be efficient to promote a global implementation by deploying more floats if the resources are available for quality control, which is the case because DeepArgo doesn't require more quality control than core Argo, because it's mostly temperature and salinity.
Nice. And feel free to loop Deuce in on getting that modeling DeepArgo meeting together if you need some help.
Okay. Yeah, no, that's actually, if there's funding for organizing this, I'm all ears.
I was just curious, Nathalie, the maps you have from where the GFDL model is having biases, how much does that line up with Sarah Perkey and Greg Johnson's map of the deep warming trend from hydrography? Because that is I feel like their work did a lot to motivate where we've been putting the DeepArgo floats in terms of trying to capture that deep signal. If we can capture it where that signal exists, that's a good sign. If we can't capture it there, we're in trouble globally, right? Which all the results that Nathalie showed that we can, we can capture that signal in the DeepArgo basins, and it's looking good. But I'm just curious, how that lines up with your model biases.
Yeah, so it's a bit tricky because the models are not equilibrated in the deep ocean. And so we don't really know if our biases are like equilibrated biases or if it's, right, because you're talking about, so the maps that you're thinking of and that I'm comparing to are the trends in deep temperature. And the trends are harder to assess in terms of biases because you don't know if the trend is like a controlled drift that's an error in your initial condition, or if it's really like a problem with the model. And so, I'm still trying to tease all of that out. And then also there's the fact that the maps that Sarah Perkey generates are using pretty substantially spatially subsampled sections. And so I think what we really need to do with the models is like sampled observations along those sections and then reconstruct the same type of apples to apples data set. Whereas if I make plots of the bottom heating, there's really large spatial variability. And so I'm worried that like subsampling would be a leading error in that comparison.
No, that all makes sense. And then I had one follow-up thing for thinking about where to put new floats. Nathalie, is there any discussion about thinking with places that we maybe don't know the bathymetry as well, or places where the bathymetry is particularly important, like places with, topographically induced upwelling in the Southern Ocean, where there's like really short times or short length scale variations in topography because it's very rough, and maybe that would be a good place to put floats to get a better idea of that small scale variability of bathymetry. Just something else to maybe think about with that.
I think, topography, bathymetry has been added to the objectives of DeepArgo, but I think it's fair to say that ocean heat content and storage sea level are the priority for now. I think I see as bathymetry as opportunistic objective because it doesn't require to add anything. We can deduce bathymetry from DeepArgo measurement without adding sensors. But you raise an important question that, in terms of DeepArgo, I think being able to resolve mixing, I think that's something that is achievable by increasing the vertical resolution of the CTD measurements. But when you're referring to timescale, I think that will be a limitation of deep Argo floats, right? Is that they sample every 10 days, and they can only, the fastest you can reach the surface, do a round trip to the surface is a day and a half. So that would be something, I think that would be some great discussion to be had with the mixing community. I talked about implementation of BGC sensors on deep. There's right now, I went quickly over this, but there's the prototype level plans to implement some microstructure sensors on some floats. It's still on prototype level. But I think, I think there's discussions to be had with modelers and with the mixing community of what is achievable, how much of the mixing in the deep ocean can be resolved using deep Argo. I mean, Mitch, I don't know if Mitch showed it in his poster yet, but he looked at mixing from deep Argo floats that was inferred along the deep western boundary current, and there's some breakthrough, I think, that will happen with the deep Argo data.
Great, thanks.
Yeah, I mean, I was going to come back to my question, and I mean, just with the caveat that I'm all for Argo. I'm for BGC Argo and deep Argo. But the funding amount that you quoted, $80 to $90 million, is a lot of money. And with the budget cuts at this point, and with the struggles that Mike and I went through for the Rapid, with MOVE and OSNAP area funding, which costs a lot less, I mean, per year basis. I mean, they are just well, I shouldn't say just trans-basin areas, but they are only covering certain regions. I think, I'm not sure how this, I mean, how can, I guess as a community, how can we help in that sense? I mean, asking directly for 80 to 90 million is a lot. And dividing into smaller chunks may or may not be successful. And as you rightly indicated, that if people are using Argo data sets, they should cite them so that you can keep track of them. But as Argo people, you have conflict of interest and vested interest in the continuation of Argo. And when you advocate for Argo yourself or that group, then that may not have as much weight as we as a community
Absolutely
for Argo.
Yeah, that's the problem. We can advocate as much as we want, but the power is to you, non-Argo people, to do it for us, because I think there's an order of magnitude difference easy between the impact that it has when we say we need Argo and when you, non-Argo people, are saying it. Absolutely.
I guess maybe as outcome of this meeting, if you can strategize on how to essentially maybe galvanize the community with society. I mean, one thing that with the Rapid and OSNAP, the question, especially with the Rapid, how is it relevant to society, right? I think having societal connection, I mean, we have seen a bunch of scientific examples of uses of Argo, which are fine, but how are they relevant to the society at the end? I think, especially at this day and age, when we are asked for actionable, societally relevant science and predictions and all that stuff, we can maybe argue that it's better initialization of the prediction systems. I think we need to somehow come up with a strategy. And then, so that's one thing that I think we can do. Another thing is that maybe instead of $90 million, and sometimes I know that it happened with, I think, Rapid and OSNAP, it's like almost like an a la carte menu. And it is, I think, coming back to what you were saying as well, what is absolutely necessary? What would be nice, what is desired and all that stuff. If we provide, or if it's maybe provided some options that can be helpful for the funding agencies also, maybe they may have only 50 million. And what can we do for 50 million? And is it really worth doing it with 50 million? Do we need the higher amount? So I think I'm just putting some things out there. I don't have a particular.
I think there's a value in having. It's just a suggestion. It's not what needs to be done, but perhaps there would be a value into considering different funding agencies, and the different funding agencies sort of like spreading the total amount and agreeing on the amount that it could contribute to. And if anything, that would be a great step forward, because it would lead to some increase, because right now we're sort of stuck. So different institutions have, put a lot of work and resources into BGC and DEEP, and core Argo is decreasing because the longevity of the BGC Argo floats and DEEP has done a lot of progress, but it's not yet to the averaged longevity of the core Argo floats. So each time you deploy a DEEP or a BGC, well, it won't quite last as long as a core. So overall, with a flat budget, you end up losing the array. So having different funding agencies, I very much like your suggestion of having a more applications of Deep Argo that is easier to relate for society. I think IFDUS could come up with a team to do that. I will be gladly, I'd be happy to contribute, but it won't be hard at all. When you're trying to, predict ocean heat content, you're trying to predict how much of the Earth's going to heat up. You're trying to predict how well we can make predictions of sea level, in terms of fisheries, in terms of coastal development, in terms of, water resources. I mean, it's not hard to do, but I agree with you that it needs to be done in a more effective way.
We'll let Lynn have the last word for now on this conversation.
Hi. I'm not quite clear about where this number of 80 or 90 million per year comes from. When I calculate what we suggest is needed for BGC Argo, the US contribution, which is half the global array, would be 100 floats per year. With operating expenses, that's 10 million a year. If Deep Argo is equal to that, that makes 20 million. And if Core Argo is a fraction of that, then we're talking 25 to 30 million a year.
Yeah, but Lynn, you're not counting, the resources for quality control. You're not accounting for
that for BGC Argo. That's the cost.
I think it's more 20 million for the US. For the 25 million for the international is closer to the total amount, but it's okay. It's big numbers regardless. No, but I think 80 million is a better estimate.
About whether we're talking about the full array or the US portion of it.
I'm talking about the full.
Yeah, so cut that number in half, Gokhan. The US has never committed to more than half.
Yeah.
And I think it's a totally reasonable number in light of computing. You're talking about one center. The US has more than one center, major modeling center. It has at least 3, correct? How many? 4, at least 4. So multiply that by 4 for the modeling component. And we're talking about, basically less than 1 modeling center. And when Core Argo went down for 1 week last year because there was a problem with NOAA paying its bill, there were outcries from operational agencies. There are paying customers for Core Argo, for TS. They don't want it down. And I don't think that one could say that we're self-interested. We're self-interested in the same sense as your portion of your facility is that maintains your computer, not the portion that includes you doing the research. This is a resource, and it happens to be parsed out amongst different academic institutions that happen to get overhead. Okay, there is self-interest from that, but we haven't found that our institutions have been very supportive of our drive to get out there and make sure this is continued. I think that we see it as a very, very valuable way to monitor the ocean, to produce the network of measurements that are global, that tie together every other system that's out there that's local. And I don't know how you move forward in oceanography. Ghost Ship goes once every 5 years with non-synoptic crossings and stations that, and it measures everything, and that's super, super important for calibration of these resources. But you talk to NOAA, they say, we need more autonomous stuff because we don't have money for ships. Well, where are you going to get autonomous stuff that's not Argo, that's going to be global? It's Argo. So I think it really is our interior observing system.
Yeah, no, I think we all agree that for what it does, it's really cheap. But I think, perhaps putting into numbers of $1 million per year, the impact that it has on the industry. it is what needs to be done, you know, how much having one Argo fully implemented impacts, you know, in terms of whether the forecast would be wrong, how would that affect fisheries, how would that affect, you know, basically not having Argo, how coming back to Lynn's comment, how much not having Argo would hurt the industry could be a good way to go about it.
And 75% of that money goes to companies, not into our.
Yeah, no, that too.
Yeah, Sarah, if you wanted to quickly unmute to voice those.
I guess I was just clarifying what Lynn was saying too about the cost and predictions about. I mean, these are all forecasts for what we think one Argo is going to cost, but it is a remarkably cost-effective way of monitoring the ocean. And I think, so I think, Nathalie, just to be clear, you're talking about one Argo, not deep, because deep's only a third of that
I was talking about one Argo International because I thought that was the question.
Yeah, one Argo International is going to be kind of that, you know, 80, 90 millions a year. But if we want to just expand deep Argo for the US, we're talking more like $10 million a year of extra funding we would need.